The Atlantic Meridional Overturning Circulation, AMOC, is a crucial component of Earth's climate system. It's part of the larger global ocean conveyor belt, transporting warm water from the tropics toward the North Atlantic and returning cold water toward the equator. Here's a detailed explanation of how to crack or understand the AMOC. 1. Understanding the AMOC warm surface currents. The AMOC is driven by warm, salty water flowing northward from the equator. This warm water travels along the surface of the Atlantic Ocean and is part of the Gulf Stream. Cooling and sinking in the North Atlantic. As this warm water reaches higher latitudes, it cools and becomes denser. The increased density causes the water to sink in the North Atlantic, a process called deep water formation. Return flow. The cold, dense water then flows southward at the ocean floor, returning to lower latitudes and eventually upwelling to the surface in the Southern Ocean and elsewhere. 2. Key components of AMOC thermohaline circulation. The AMOC is driven by differences in water temperature, thermo, and salinity, halin. Warm, salty water is lighter and remains on the surface, while cold, salty water is denser and sinks. Gulf Stream. A major part of the AMOC is the Gulf Stream, which carries warm water from the Gulf of Mexico up the eastern seaboard of the United States and across the Atlantic Ocean to Europe. North Atlantic Deep Water, NADW. This is the cold, dense water that sinks in the North Atlantic and drives the deep southward flow. 3. Factors influencing the AMOC salinity. Changes in salinity, particularly due to freshwater input from melting ice sheets or increased rainfall, can affect the density of seawater and disrupt the AMOC temperature. Global warming leads to warmer ocean surface temperatures, which can reduce the cooling effect in the North Atlantic, weakening the AMOC wind patterns. Wind stress affects ocean currents and can influence the strength of the AMOC. 4. Consequences of AMOC disruption. Climate impact. A slowdown or collapse of the AMOC could lead to significant climate changes, including cooler temperatures in Europe, changes in monsoon patterns, and shifts in tropical rainfall. Sea level rise. A weakened AMOC could lead to regional sea level rise along the U.S. East Coast due to changes in ocean currents. Ecosystem changes. Changes in ocean circulation can affect marine ecosystems, fisheries, and the distribution of marine species. 5. Monitoring and predicting AMOC observations. Scientists monitor the AMOC using a combination of satellite data, ocean buoys, and ship-based measurements to track changes in temperature, salinity, and current strength. Modeling. Climate models are used to simulate the AMOC and predict how it might respond to various climate scenarios, such as increased greenhouse gas emissions or large freshwater inputs from melting ice. 6. Current research and debate. Strength of AMOC. Recent studies suggest that the AMOC has weakened over the past century, potentially due to climate change. However, there is ongoing debate about the extent of this weakening and its future trajectory. Tipping point. There is concern that the AMOC could reach a tipping point, where a sudden and irreversible collapse could occur. Researchers are working to identify early warning signals of such an event. 7. Cracking AMOC through research. Paleoclimate data. Understanding past changes in the AMOC through ice cores, sediment records, and other proxies helps scientists predict future changes. Climate experiments. Researchers use controlled experiments in climate models to test how different factors, for example, CO2 levels, freshwater input, affect the AMOC. Interdisciplinary approaches. Collaboration between oceanographers, climate scientists, and modelers is key to advancing our understanding of the AMOC and its role in the global climate system. Conclusion. Understanding and cracking the AMOC involves a multidisciplinary approach, combining observations, modeling, and theoretical work. The AMOC is a complex system with significant implications for global climate, and ongoing research is crucial for predicting and mitigating its potential impacts.